Good morning. We are NERDGuys, and today we are presenting the architecture design from our Assignment 3 report. Serverless and event-driven cloud architecture. Our project focused on migrating a large application to the cloud with a clear focus on achieving maximum elasticity, resilience, and cost optimization. The three pillars of modern cloud design. This report and presentation detail our decision-making process for building a platform that is ready to handle exponential user growth. We will walk through the business challenges, our true flow serverless solution, our technical justification, and the advanced implementation details we use to ensure the platform is robust. Well, move to the core challenge. We begin with the core challenge, the client's existing infrastructure based on traditional virtual machine or IaaS suffer from two major pain points: inefficiency and a serious scaling problem. From a cost perspective, IaaS leads to wasted money. When usage is low, we are still paying for idle servers that are running 24/7. We need a true pay-per-use model. From an operational perspective, scaling is slow, manual, and often breaks when certain traffic spikes occur. This means poor user experience and lost revenue. Our architecture mandates were therefore clear: cost optimization, implement a system that can scale to zero, eliminating idle costs. Extreme scalability, handle certain unpredictable traffic spikes instantly. And third is future-proof design, build a secure, decoupled, and reliable foundation. Okay, next to the serverless shift. To address these mandates, we choose a radical shift away from managing servers toward a serverless model. This is the foundation of our solution overview. The core of our compute layer is serverless, specifically AWS or function as a service, FaaS. With FaaS, we upload our code. AWS manage all the scaling, batching, and provisioning. The huge benefit here is that we only pay when the code is actually running. This directly satisfies the cost optimization mandate. The second core concept is event-driven architecture, EDA. In this model, every action like a user uploading a file is treated as an event. Our services are decoupled, meaning they simply react to these events. This is powered by Amazon SQS, our decoupling hook, or our higher level components are focused on serverless primitives, API gateway for access control, Lambda for logic, DynamoDB for scalable data, and S3 for durable object storage.
So, good morning, Mr. Jerome and fellows. My name is Hill, leader of the team, and continue the part that is in our architecture. We have three flows. So, first of all, that is user access and metadata mechanism. As you can see, that is the overall structure architecture. So, let's dive to the first flow. So, in the first flow, you can see that this flow is dedicated to handle immediate low latency user interactions and about execution and logic. On request pass through the API gateway, I will secure single entry point to Amazon Web Service Lambda, and it executes the lightweight business logic such as authentication and crucially generating the precise URL. And about the data performance, All metadata is stored in Amazon DynamoDB, which ensuring performance efficiency by providing consistent single-digit millisecond latency regardless of scale. And in this phase, in the first flow, we have core pillar apply including security by using precise URLs with for strict security rules. The client uploads the heading file directly to S3 in the second flow completely bypassing our Lambda transfer and API gateway, thus minimizing potential attack surface and reducing load on the compute layer. And of course, second is cost optimization. Since Lambda handles only the lightweight orchestration, not the data transfer, we keep our compute cost extremely low, maximizing the pay-per-execution benefit. So that's about the first flow. Move to the second flow. That is about asynchronous task processing flow, about the event-driven. So in the next flow, this is the heart of our resilient desire for having long-running tasks. So first of all, about event trigger. Once the launch media file lands in the Amazon Simple Socket storage, Amazon S3, it fires the event notification to the Amazon SNS. And this event-driven approach ensures the separation of the concerns. Next is about the coupling and durability. The event is immediately sent to the Amazon Simple Queue service, Amazon SQS, acts as durable, highly available buffer, and this is the key for reliability, as the message is never lost, even if our workers are offline or overwhelmed. And the last is execution and scaling. Our elastic container service ECS, all Lambda workers consume messages from SQS, and as a result, this spoon-paste model allows the worker and compute resource to scale independently of the upload rate. About the computer applied in the second flow, that is reliability. The SQS queue guarantees that no processing job is ever dropped, making the system highly fault-tolerant and maximizing reliability. And we also implement a phased technology here to ensure that if a worker fails or retries, the task executes exactly once, preventing data corruption. That is about second flow, and then the last one is the real-time status update. So in this case, we concentrate on DynamoDB streams and WebSocket. So about reactive mechanism, when the processing task updates the status in DynamoDB, DynamoDB streams instantly captures state change. This is a highly efficient reactive approach to propagating data changes. And second is push notification. A dedicated Lambda function is triggered by the stream. This Lambda then uses the API gateway WebSocket connection to push to the final status update directly to the user's screen. And the core pillar we applied in the third flow is the performance efficiency and operational excellence. This push mechanism eliminates client-side polling, which significantly reduces the workload on our API and database, thus boosting performance efficiency and saving compute resource, contributing to the cost optimization. And about the huge benefit in here is by leveraging streams, a WebSocket will ensure the system is highly interactive, giving the user instantaneous and accurate feedback on its job status. So our next part will be by Betan.
To meet the 3-point technical question criteria, we must justify our specific AWS service choice. First, AWS Lambda for compute. The choice was made for cost and elasticity. Lambda is the purest form of FAAS, enabling us to truly scale to zero and eliminate paying for idle server time. Second, DynamoDB for database. We choose this NoSQL database because it offers consistent, low latency performance at literally any scale, without us ever needing to manage database clusters or worry about sharding. It is inherently serverless, aligning perfectly with our cost model. Third, SQS for decoupling. SQS provides message durability. It ensures that once an event is triggered, the task is safely stored and will be executed, providing a critical layer of fault tolerance. And now to our technical deep dive. For maximum technical score, we address three critical complexity areas found in distributed systems. First, DynamoDB access pattern. Since DynamoDB is NoSQL, we couldn't use traditional queries. We proactively designed the schema to utilize global secondary indexes, or GSIs, which allow us to efficiently query the database on different access patterns. For example, finding old files blocked by a user without costly table scans. Second, distributed tracing with X-ray. In a system with Lambda triggering SQS worker, troubleshooting can be a nightmare. We implemented AWS X-ray across all components. X-ray gives us an end-to-end trace map, visually showing where latencies occurs and allowing us to debug the asynchronous flow in minutes, not hours. And third, ensuring idempotency. SQS guarantee at least once delivery, meaning a message might be processed twice. To protect data integrity, we build in deduplication IDs in our processing logic. This ensures that every single long-running task is executed exactly once, preventing duplicating processing and data corruption. These deep dives demonstrate that we consider not just the happy path, but the operational resilience of the entire platform. And now onto our conclusion. In conclusion, our serverless and event-driven architecture directly fulfills all initial business mandates. Elasticity is solved by our Lambda, cost is solved by a pay-per-use model, and resilience is solved by the SQS decoupling. The result is a highly efficient, future-proof, and optimized cloud platform. We are confident in this design provides the necessary foundation for exponential growth. Thank you for your time. We are now open for questions regarding DynamoDB indexing, extra usage, and cost breakdown of our proposed architecture.